Hello friends, welcome to Susan and John MathTube. And in today's video, we'll be learning about eigenvalues and eigenvectors. And like in the last video, let's start with the square matrix. Okay, so let A be a square matrix. And in the last video, we learned that matrix can be used as transforming functions, or matrix can transform vectors into other vectors. Okay, and in today's video we'll be learning about a special transformation, or we are trying to find some special vectors, and the specialty is even after the transformation the direction will not change. The vector will change its length, or it may change its length, but its direction will not change. So we are going to pick out a few vectors which do not change their direction, but there may be change in length even after the transformation. And if you had watched that last video, the theory video, the small video, you will understand that this simplifies to a homogeneous system of equation a minus lambda I of x equal to 0. And when we learn homogeneous equation, we learned that homogeneous equations will always be consistent. So it can have unique solution, or it can have infinite number of solution. But the unique solution is a trivial solution. What do you mean by trivial? Trivial means the solution which is of not much importance, and it's like too obvious. Look at this, the unique solution will be x equal to 0. Look, x equal to 0 means 0 equal to 0, so it's not a big deal. So we don't care about the trivial solution. We want the infinite solution. And we took a little bit of theory from your high school. Long back you might have learned that a system will have infinite number of solution if the determinant is singular. The determinant singular means the determinant will be equal to 0. Okay, so when you equate the determinant to 0, you're going to get infinite number of solutions, not the unique solution. Now, once you simplify this, or once you expand the determinant, you're going to get an equation in lambda. And like I told you in the last video, if it is a matrix of order 2, I mean a square matrix, this is a square matrix. If it is a 2 by 2 matrix, then you will get a quadratic equation. If it is a 3 by 3 matrix, then you will get a cubic equation, etc., etc. And that equation is called the characteristic equation. And if you solve for lambda, we will get eigenvalues. So what do you get? Eigenvalues. That means that change in length factor. And using those eigenvalues, we will be trying to find our x. And those values are called, I shouldn't say value, those vectors will be called eigenvectors. So I'll repeat once more. Let A be a square matrix. And here we assume that the matrix are transforming functions. And we are trying to find some special vectors. And if you ask me what is the speciality is even after the transformation, the vector will not change its direction. Only the scale will be changed. And this simplifies to a minus lambda of x equal to 0, a homogeneous system. And we are trying to find the condition for infinite solution, or we are trying to pick out lambda so that we will get infinite solution, because the unique solution is a trivial solution. And the condition is very simple. you find determinant A minus lambda equal to 0. Okay, now let's do one problem and try to understand. So please note the question. Find the eigenvalues and eigenvectors for the matrix A is equal to, okay, please note down this matrix. Now look at this. The first thing we do is we find A minus lambda I. Okay, first I'll explain the logic, then I'll give you a shortcut. So look at this. A is the given matrix and minus, I think you remember the identity matrix, and what we do is we write 1 0 0 0 1 0 0 0 1. Now you have to multiply by lambda. When you multiply a matrix by a constant or a scalar, you have to multiply each and every element. So basically what happens is this 1 and this 1 and this 1 will get replaced with lambda. Okay, now we have to perform subtraction. So I'll fill this thing 2 2 0 2 1 1 minus 7 2 minus 3. And when you subtract, you will notice that the first element becomes 2 minus lambda. But there will be no change for the second one, the third one, and the first element in the second row. But this will change. And finally, this will also change. So what I'm trying to do is, I'll try to write A minus lambda I in a single step. And since I'm after the determinant in such a way that it will be equal to 0, I'm going to write the characteristic equation is given by determinant A minus lambda equal to 0. And in the next line itself, I'll write the determinant. And it's really easy. You'll just take a look at the leading diagonal. And you write 2 minus lambda, 1 minus lambda, minus 3 minus lambda. And all the other elements will remain the same. Now it's your job to expand the determinant. In the next video, I'll give you a shortcut to find the characteristic equation without determinant expansion, because I've seen that some students struggle with the expansion part. Anyway, I have a shortcut for that. So usual expansion plus minus plus, so it will be like 2 minus lambda times, you have to multiply these two. So 1 minus lambda, and I'm going to take minus common, so it will be 3 plus lambda minus 2. Now the next one, minus 2 into, that will be, I have to multiply this and this. So I'll multiply right away. That will give me minus 6 minus 2 lambda. Minus minus will be plus 7. And good news, it's 0, right? So plus 0 is equal to 0. Now I have to simplify. So 2 minus lambda times, okay, I'll put minus outside, I have to multiply, okay, so 3 plus lambda, then this minus 3 lambda minus lambda square minus 2 minus 2 into, okay, that will be 1 minus 2 lambda equal to 0, and that is 2 minus lambda and we are going to get minus 3, and this will be minus 2 lambda. So when this negative goes inside, it becomes plus 2 lambda and plus lambda square minus 2, and that this part will be minus 2 plus 4 lambda equal to 0, and that is 2 minus lambda, and you're going to get lambda square. I'll write this first, and then plus 2 lambda, and finally minus 5, minus 2 plus 4 lambda equal to 0. Now again I have to multiply by 2, so that is 2 lambda square plus 4 lambda minus 10 minus lambda cube minus 2 lambda square plus 5 lambda minus 2 plus 4 lambda. This has been waiting for a long time. Okay, so that is minus lambda cube, and then so these two will get cancelled. So I'm going to write plus 0 lambda square. Now lambda and this one. So 4 plus 5 9, 9 plus 4 13. So that will be plus 13 lambda, then minus 10 minus 2, so minus 12 equal to 0. If you want, because some people would really love to have the first term positive, so you can multiply throughout by negative and make it 0 lambda square minus 13 lambda plus 12 equal to 0. But since you're going to use a calculator, it doesn't make much difference. If you want, you can leave it as such. Anyway, this is called the characteristic equation. Look at this. I told you, if the given matrix is of order 3 by 3, then the characteristic equation will be cubic. Now use a calculator and solve for lambda, and that will be our eigenvalues. So take a calculator and solve. So the eigenvalues are lambda equal to minus 4, 3, 1. Okay. So half the job is done. So we have found the eigenvalues. Now we are planning to find the second part, the eigenvectors. And now look at this. This is type 1. Type 1 in the sense all the eigenvalues are distinct. In the coming videos, we'll be doing problems where 2 of them are equal and all the 3 are equal. Now look at this. In the next video, I'll give you a shortcut. Look at this. We wasted a lot of time doing this determinant expansion. But there is a shortcut which will give you the equation right away. So, did you note the eigenvalues? 4 lambda equal to minus 4, 3 and 1. Okay, now let's go for the eigenvector. So, I hope you remember, if x is an eigenvector, then what will be the transform of x? Yeah, lambda times x. And on simplification, what do you get? A minus lambda I of x equal to 0. So this is exactly where we start for the eigenvectors. And I'll do one thing. I'll note the eigenvalues here. Minus 4, 3 and 1. So let's start with lambda equal to minus 4. So we'll write case 1, lambda is equal to minus 4. Now I'll just plug in that minus 4 here. So I get a plus 4I of x is equal to 0. And I hope you remember the given matrix. I'll note it here for you. The given matrix is 2, 2, 0, 2, 1, 1, minus 7, 2, minus 3. Okay, now I gave you a trick long back in the beginning of the video. So if you want a plus 4I, but remember this is a matrix, you can do it right away. All you have to do is add this 4 in the leading diagonal and keep all the other numbers same. So what is 2 plus 4? 6. And the other numbers are same. Now look at this, the leading diagonal. Now what is 1 plus 4? Yeah, 5. And the other numbers will remain same. Now the last one, what is minus 3 plus 4? That is 1. And let's assume our required eigenvector is x1, x2, x3. And the right side is equal to 0, 0, 0. Now look at this. The guarantee is we found lambda in such a way that this homogeneous system will give us infinite solution, not the trivial solution, infinite solution. So we are already aware that we are going to get infinite solution here. Okay, now I have a shortcut for you. The shortcut is you choose any 2 rows you like. You choose any 2 rows you like. Anyway, I'm going to choose the second row and the third row. And then we will apply something called rule of cross multiplication. And it's very simple. All you have to do is you have to write x1 by, look at this, you leave this part and take the determinant of the remaining part is equal to x2 by, you leave the middle part and take the determinant of the remaining part 2, 1, minus 7, 1 and put negative outside. And finally x3 by determinant, so leave this 1, 1, so write 2, 5, minus 7, 2 is equal to some constant. I'm going to put it equal to k. Now that gives me x1 by, so 5 minus 2 is equal to 3, and x2 by, so 2 plus 7, that will be 9, but that negative makes it minus 9, is equal to x3 the whole divided by 4 plus 7 into 5, that is 35, that will be 39 is equal to k. Now I'll equate the first and the last. So I'm going to get x1 is equal to 3k and x2 is equal to minus 9k and x3 is equal to 39k. So the required eigenvector corresponding to lambda equal to minus 4 is, I can just cancel this common factor. So I'm going to write 1, minus 3 and 13. So this will be capital X1. So what I did is I took common factor 3k. So you can cancel 3k, 3k, 3k. Okay. Now look at this. So the eigenvector corresponding to lambda equal to minus 4 will be 1, minus 3, 13. Or all the vectors parallel to this. It's a huge system because you can write 2 minus 6, 26. You can write 3 minus 9, 39, etc., etc., etc. Okay, now we do the same thing. So I'll write case 2, where lambda is equal to 3. And we start with a minus lambda I of x is equal to 0. And that will be a minus 3i of x is equal to 0. Okay, I have put a over here. Now, what's the trick? Yeah, all you have to do is you have to subtract 3 along the leading diagonal. So 2 minus 3, that is minus 1, and the remaining will be same. And 1 minus 3, that is minus 2, and the remaining will be same. And minus 3 minus 3, that is minus 6. And I'll assume my eigenvector to be x1, x2, x3. And of course, the right side 0, 0, 0. Okay, now I told you I have a trick. And the trick is called rule of cross multiplication. You can use any 2 rows you like. Anyway, I'll stick to the second row and the third row. So what I do is I'm going to write x1 by determinant. So look at this, you have to focus here. So when I write x1, I'll forget about this part and I'll write minus 2, 1, 2, minus 6. And that is equal to x2 the whole divided by, don't forget this minus which is outside. So 2, 1, minus 7, minus 6, and is equal to x3 the whole divided by, and that will be 2 minus 2 minus 7, 2 is equal to k. And on simplification, I'm not going to waste your time, you will get x1 is equal to 10k because 12 minus 2, and x2 is equal to 5k, what do you call, minus 12 plus 7 and the negative outside, and x3 is equal to minus 10k. That will be 4 minus 14. And I'm going to write the second eigenvector, and I'm going to write the second eigenvector to be capital X2 is equal to, I'll just cancel all the common factors over here. So I'm going to get 2, 1, minus 2. Or you can write like this. The second eigenvector is the parallel system or the system of vectors parallel to 2, 1, minus 2. And let's go for case 3. Same thing. So I'll reduce the steps. Here lambda is equal to 1. So a minus lambda x. So that will be here lambda is equal to 1. So a minus lambda I of x is equal to 0, but lambda is 1. Now the shortcut, all you have to do is diagonally subtract 1. So we get 1, 2, 0, 2, 0, 1, minus 7, 2, minus 4, and x1, x2, x3 is equal to 0, 0, 0. Okay, now as usual, we can apply a rule of cross multiplication. I'm going to choose the last 2 rows. So x1 by determinant 0, 1, 2, minus 4 is equal to x2 by, don't forget this negative, 2, 1, minus 7, minus 4, and that will be equal to x3 by determinant 2, 0, minus 7, 2 is equal to some constant. Simplify, we will get x1 is equal to minus 2k and x2 is equal to k, and x3 is equal to 4k. And the third eigenvector will be x3 is equal to minus 2, 1, 4. Okay, so that's it. In the next video, I'll be back with more problems in eigenvalues and eigenvectors. And the first thing we're going to do is we're going to learn a shortcut method to find the characteristic equation so that we can reduce the time. And after that, we'll be dealing with repeated eigenvalues. So I'll be back. Till then, bye.